Find the shortest route between these cities. With just a few, it's easy. You can simply check them all. But add more cities and the number of routes explodes, past thousands, past billions, past the number of atoms in the entire universe. A puzzle simple enough for a child to grasp, yet one that no computer on Earth can solve quickly for large maps. How can that be? Here are two puzzles. They look almost identical. On the left, visit every city exactly once and return home by the shortest path. On the right, travel every road exactly once, never repeating one. One of them a child can solve in an afternoon. The other has defeated the most powerful computers in the world. The only difference, whether you care about the dots or the lines. Let's start with the easy twin, the lines. In 1736, the city of Königsberg had 7 bridges and 1 challenge. Take a walk crossing every bridge exactly once. Try it, start anywhere, cross a bridge, then another. But no matter how cleverly you plan, you always get stranded, 1 bridge short. Every time. Euler saw why. Think of a piece of land you only pass through. Every time you arrive, you must also leave, and that uses bridges 2 at a time. So such a land needs an even number of bridges. But in Königsberg, every landmass has an odd number. So the walk simply doesn't exist. Only the start and the end may be odd. The rule, the walk exists only if 0 or exactly 2 landmasses are odd. One glance, and you know. That single idea gave birth to the entire field of graph theory. Now the hard twin, the dots, the traveling salesman, a handful of cities. Start at home, visit each once, return, which route is shortest. With a few cities, you can measure every option. This route is longer, this one shorter. Keep the best. Easy, so just check them all, for 5 cities sure. How many options are there? From home you pick the first city, say, 7 ways. Then 6 remain, then 5, and so on. Multiply them together. That's a factorial. Then divide by 2, because every route is the same forwards and backwards. For n cities, n-1 factorial divided by 2. 5 cities, 12 routes. 10 over 180,000. 15, 43 billion. 20, 60 quadrillion. Put that in time. Checking a billion routes per second. 10 cities, instant. 15, about a minute. But 20 cities, nearly 2 years of nonstop computing. At 61 cities, there are more routes than atoms in the observable universe. Every computer ever built, working together since the Big Bang, still wouldn't have checked them all. Maybe there's a shortcut, a clever formula that skips the search. For nearly a century, the brightest minds have looked. And here's the strange heart of it. If I hand you a finished route, you can check its length in seconds. Easy to verify, but finding the best one out of them all seems impossibly hard. Easy to check, hard to solve. That gap has a name. The traveling salesman is NP-hard. And whether easy to check always means easy to solve is the famous P versus NP question. A $1 million millennium problem, still open. This isn't a new puzzle. In 1954, Danzig and his colleagues solved a route through 49 cities by hand. By 2006, researchers found the optimal route through 85,000 points. We win battles. But the war, the general problem, stays unsolved. So how does the world cope? We stop chasing the perfect and chase the good enough found fast. Heuristics. The simplest, always drive to the nearest unvisited city. Quick, intuitive, but greedy. It traps you, one long, painful leg at the very end. And greed has a price. This nearest neighbor route is often about 25% longer than the truly best. Fast is not the same as good. But we can fix it. Find 2 roads that cross. Swap their ends, and because a straight line always beats a detour, the total can only shrink. Uncrossing never hurts. So we hunt for crossings and undo them, again and again. A tangled route relaxes into something short and elegant. Now the scale. 100 cities, far beyond brute force. Start with a rough, greedy route. Then uncross, and the chaos settles into a near-perfect route in seconds. Almost 20% shorter than where we began. And this powers the world. The same problem routes deliveries, drills circuit boards, sequences DNA, schedules telescopes. And scale is everything. A delivery giant with millions of stops a day. Shaving routes by 1% saves hundreds of millions of dollars and millions of gallons of fuel. The salesman is everywhere. And beneath it all sits that million-dollar question. If anyone ever proved P equals NP, logistics and medicine would transform, and much of the encryption guarding the internet would break. Most bet it's impossible. No one has proven it. So sit with this. Cross every line. A child's puzzle solved in 1736. Visit every dot, one of the deepest mysteries in science. Two puzzles almost identical. The simplest questions can hide the hardest truths. And sometimes the most human thing we can do is find a route that's good enough and get going.